This question, hold on, let me make sure my microphone is on. Okay. This question was actually the bane of my existence, and I really hope that you know that. The pair of capacitors in the figure below are fully charged by a 24-volt battery. The battery is disconnected, and the switch is then closed. I don't even want to know. This was 10F number 6, I think. This was just hell. I just want you to know that beforehand. Do little arrows. This is going to be our positive. This is going to be our negative. Positive, negative. Bam, 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 bam. And then this circuit is going to be closed. Pass through our 500 ohm. After 30, so question A, after 30 milliseconds has elapsed, how much charge remains on the 3 microfarad capacitor? Here and here, those are the 2 capacitors and their amount. Before we get started, loop rule. Sum of voltages equals 0. Okay, I'm gonna kind of look over this as like a whole. I just want to reiterate how awful this kind of was. So we only needed to use this equation, we needed to use it for here. So milliseconds, time constant is what immediately we should be thinking. So Q, charge over capacitor, minus the current times resistance equals 0. So the charge, current is just the charge like per time, or change in charge per time, times the resistance. So I just changed that. And then, because it was 0, added it to both sides. And then I made myself a little differential equation here. Integrals, my favorite. So our bounds are going to be from Q to the small q, and then dq over q equals integral from 0 to time, whatever the time is, dt over rc. And so we take the integral of this, and it's going to turn into the natural log of q, q to q equals, I should have differentiated that up there, but it's whatever. And then this here is going to turn into bam, bam. It's just going to turn into negative t over rc. Bam, 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 from 0 to t. This is going to turn it into the natural log of q minus the natural log of uppercase Q equals negative t over rc, because there's nothing. We know with natural log, if you subtract them from each other, it's whatever's the negative, it's going to go on the bottom of our fraction here, and so it turns into natural log of q over q, lowercase q over capital Q, equals negative t rc. Natural log, to clear this, we clear that this is going to turn into e, which is constant, of q over q equals e to the negative t over rc, and then we multiply the capital Q on both sides, and we get this, which we have seen before, and this is when it goes from 0 to infinity, I believe. Yes, from 0 to infinity. So this is our final equation that we get. We can push this off to the side for now. Change in V equals Q over C, charge over capacitance. This is going to be a mess, I'm sorry. So the total charge equals charge 1 plus charge 2. We don't know charge 1 or charge 2, but you know what we do know? We know capacitor 1, capacitor 2. So we're going to do something with this. Again, in my previous video, which I did today, I set up something very similar right here. But in order to even start to start working on this here, we are going to find this. Because, again, I'm going to do that substitution for Q1, I believe it is. But I need to find the total charge. we know delta V equals charge over capacitance. And this is going to be total capacitance. So our change in V, delta V, is going to be 24 volts. So 24 volts equals charge over 3 microcoulombs plus 2 microcoulombs, and that's going to equal 1.2 times 10 to the negative 4. Oh, I'm sorry. Coulombs. And so, okay. So we figured out our total charge, right? Now, we're going to put this into over here. So to figure this out, Q1, I did it to the side again, I'm sorry, this is so messy, but Q1 equals 1.2 times 10 to the negative 4th coulombs minus Q2, bam, bam, subtract from both sides. You know how it is. I set this up. Hold on, I'm sorry. Let me think about how I set this up. 2.4. Oh. I put this into here. So it's going to be 1.2 times 10 to the negative 4th minus 2. I set up my equation. I kind of skipped ahead a lot. So 2 is going to be multiplied, 2 microcoulombs is going to be multiplied up here. I just did that, 2.4 times 10 to the negative 10th coulombs minus, and then it's going to be 2 just times Q2 right there, minus 2 times right there. And then this multiplied by that. Same deal again, 2.4 times 10 to the negative 10th coulombs equals 3 coulombs Q2 plus 2 microcoulombs C. 2 microcoulombs times Q2. We're going to move it all to one side because we want to isolate Q2. That's supposed to say. There we go. Q2. Did all that math, and I got the grand total answer of 4.8 times 10 to the negative 5th coulombs. So this is going to be our first, our charge 2 right here, and I just plunked that right back into this equation to find, oh, I was right, this is supposed to say Q1. There we go. And so I just flunked that back into the equation, and for Q1, I got 7.2 times 10 to the negative 5th. Oh my gosh, took a kabajillion years, and that's just the beginning. We haven't even started the problem yet. So this equation that we integrated and derived, we kind of did it all. No, it's just integrated. We're going to now use that right here for part A. So Q of T equals capital Q e to the negative T over RC. And this is after 0.30 milliseconds has elapsed. This is just focusing on the 3 microfarad capacitor. So using the equation that we derived, our time is going to be 3 times 10 to the negative 3rd seconds. That's literally 0.03 milliseconds. Equals 7.2 times 10 to the negative 5th coulombs, which we got from right up here. E times e to the negative 3 times time again. Over 500 ohms times 5 microfarads. And remember, 500 ohms. And so these are in parallel. I never explained why. These are in parallel here. So we can just add these up. It's going to become one huge resistor. So you just add them up. Or one huge capacitor. Oh, gosh. There we go. That's how we got that equation. Plug that into my calculator. Plug and chug. 14.5 microcoulombs is what I got. 21.7 microcoulombs is what I got. I'm on the wrong thing here. Now we do the exact same process to find C2, to find charge number 2, little charge number 2, and that's going to be 4 we're going to use this one right here. Bam, bam. 4.8 times 10 to the negative 5th, e to the negative 3, e to the negative 3 times 10 to the negative 3 over 500 ohms times 5 microfarads. You know the drill. Plug that into my calculator, and that's where I got 14.5 microcoulombs. What a drag, you know? So we figured out part A and B. Finally, right? A, B. Part C asks, what is the current in the resistor at this time? Current V equals IR. We've known this. We've been known this. But we need to figure out the new voltage because it's changed after oh my god, okay, hello. The battery is disconnected. Obviously, we see no battery here. We have no voltage right now. But what we just solved for, this is after it's removed, so it's been changed. Voltage has been changed, and then the switch was closed, meaning the charge would slowly leak out of both of the capacitors at the same time. So V equals Q total over capacitor total, which is just going to be, so we added this and this. Did we add that in that? 3. We did add these two together. I just put the wrong decimal place there. It's okay. Okay, so we get 3.61 when you add these two over 5 microfarads, and that's going to equal 7.22 volts. And so obviously our voltage has gone down quite a bit. Quite a bit actually. So then we plug this into here, into there. So V equals IR. 7.22 volts equals 1 times 500 ohms, because we know that that's a resistance. It's the only resistor there. Now divide both sides by 500, and our current should be 0.01446 amps. I hated this question. I'm just gonna say it. This entire thing, bane of my existence, I would just like to say, I didn't even know how to start this at first. I'm like, wait, V, okay, that's Q over C. And then, but the V equals IR too. So we needed to have both of those here. I'm just going to show that. So V equals Q over C, and V equals IR. We set this equal to each other. Q over C equals V equals IR. And that's how we got this right there. So that confused me. And then right on our next step, I was like, what in the world? I have two unknowns, and I don't even know where to start to figure out this. And this was all leading up, by the way, to like an equation that we've already known. But I had to prove that I knew it. Semi. So I finally figured that out. I went through. I do, sadly, know how to do integrations, whatever it's called. And then this was a whole separate problem, because now I'm trying to figure this out, and then I need to incorporate it back into this and and oh my gosh, it was a mess. You can see my thought process here. It was really bad. So I start off with this, and then I turn it into this, because I know that I'm gonna need to set it up like that. But then I'm like, oh wait, I need to figure out the total charge, and then the total charge is gonna help me get the first charge and the second charge. But I need to set that up, and then I need to go here, and then back to here, and it's this whole thing. And then we go back down here, and then we figured this out, and then plug it back in, and then we go back here, and plug that back in, and then we finally get our total answers, and we haven't even started the problem yet. Then we finally get to the problem. Whatever, plug everything in, da-da-da-da-da. Oh, at first, because it was only, we were only doing Q1, at first I was like, oh, it's only C1. Absolutely not. And I was wrong. And then I got Wahoo. Then we did the same thing. And then for this here, I did that math. Or I just kind of, I had a brain fart there for some reason. But I think it's the friends that we made along the way. I do actually now understand how this works. It's just, this confused me. Always like with the switches, they're kind of confusing me. I'm going to be so real with you. And RC Circuits and I think we're going to have some personal beef after this is all over. Yeah. Thank you for listening.